Alright, so let's go through the 12th of 10th, 2019 A-level question. So for part A, right, state the conditions required for a body to be in equilibrium. So this one is the stable equilibrium, meaning that, okay, first, to be in translational equilibrium, the object must have no resultant force. So the F right here is the resultant force. Okay, then for the second one, rotational equilibrium, the clockwise moment is equal to the anti-clockwise moment about a pivot at any point. So these are the two conditions. Okay, for part B, let's go to the part B first. Okay, a person of weight 700 Newton is at rest, right, from a point on the wire. So the weight of the wires are negligible. So we are asked to determine the magnitude of T1 and T2. Okay, so 4 marks this one, so it's a bit more tedious. Okay, first, we know that there's no resultant force in the horizontal and the vertical direction. So let's determine the vertical directions first. So we have a downward force of 700 Newton. So the T1, right, is diagonal, then the T2 is also diagonal, meaning that you can resolve into the vertical and horizontal component. So let's resolve to the horizontal first. Vertical first. So vertical is T1, right? So T1 sine 20. Now, why is it T1 sine 20? Is because if you think about this, right? So this is the T1. Always remember the T1, the so-called the force, is always the hypotenuse. Then this one is the horizontal. If this is a horizontal, meaning it's pointing towards the left-hand side, means that there's a vertical component. So vertical component apparently, right, is your opposite. So the what is it called? The T1, right, is your hypotenuse. So so right, you want the so meaning that you want the sine. So sine 20, so this is 20 is equal to oppo over hypo. So that's why oppo, right, is in terms of T1 and sine, right, is actually T1 sine 20. That's it. Okay, what about T2? Okay, T2 same thing. You want the vertical component. So this one is your T2 sine 10. So these two things add up will be equal to your 700, because total upward must be equal to total downward. So you must first write first. So T1, okay, I write here first. So T1 sine 20 plus T2 sine 10. So this will give you 700 Newton. Okay, so that is the very first equation. Okay, what about the second equation? Okay, T2. Okay, second equation, horizontal. We look at the horizontal, right? So apparently there's no horizontal resultant force. So meaning that if you look at T1 there's a horizontal force in this direction, left hand side. Then the T2 there's a horizontal in the right hand side. So meaning that this and this must cancel out each other. So let's determine our horizontal component of your T1. So T1, same thing, you want the adjacent, because let's just say I write here. So this is adjacent. So tuaka, so right. So this will be cosine. So cosine 20 is equal to a j over hypo. So a j is equal to T1 cos 20 degree. Meaning this part will be T1 cos 20. Then what about the T2? The horizontal component. Okay, horizontal component T2 cosine 10 degree. So this thing and this thing, right, they must be equal. So that will be the second equation. So T1 cosine 20 is equal to T2 cosine 10 degree. Okay, so then now my intention is to make this is the second equation, right? So you can see there's actually a simultaneous equation. So I want to make T1 the subject. So T1 is equal to T2 cosine 10 over the whole thing over cosine 20 degree. So it's equal to, let's see, cosine 10 divided by cosine 20. So I leave it in terms of T2 So T1 is equal to 1.048010521 T2. So this one is T1, right, is equal to this. So meaning that I go back to the so-called the first equation. So first equation I just sub inside now. So this thing, right, this whole thing here, you put inside here. Okay, so what you get is actually 1.04801052 T2 times sine 20 is equal to plus T2 sine 10 is equal to 700. Okay, so now it's time to solve for T2 first. No? So, okay, times sine 20. Okay, so this part will be 0.358440708 T2 plus. So sine 10, right? Sine 10, I just calculate. So 0.173648177 T2 is equal to 700. Okay, so the next part is just to solve for the thing. Just that it's a bit too many numbers already. Plus 0.358440708. Okay, so I write here. Okay, so this part will be 0.532088885 T2, right, is equal to 700. So meaning that I just solve. So this one bring over 700. Okay, so your T2 roughly 1315.569672. Yeah, I double check first. Wait, 32048. Okay, can. So is roughly equal to 1320 Newton. So that is for T2. 1320 Newton. Okay, what about T1? Okay, T1 is a simple one because I already know, but I already know my T2. So if you look at this, right, so just sub inside. So since I know T2, just sub inside. So T1, yeah, right here. So T1 is equal to 1.3. Okay, I use this thing times 1.04801051. So you times T2, meaning T1 is equal to 1378.73, so and so forth. So just put 1380 Newton. So that is how we solve. 1380 Newton. Okay, so with this, I'll move on to the next part, C. Okay, part C, we have this very complicated diagram. So we have two forces, right? So first will be the wire from here, then the other will be the support cable. Alright. Okay, so let's see what they want from us. So we have a cable attached 1.2, etc. The tension of the wire is 150. So the whole thing is in equilibrium. So calculate what is the tension in the support cable. Okay. So for this question, to be frank, you can actually use the resolving of your vectors. But for me, I just use the POM to solve, because POM very fast one. So of course, to use POM to solve, you must make sure that you put a pivot somewhere. So where should we put a pivot? Okay, for the pivot, I put it right here, the base of the pole. Okay, the next thing is I must know that my CW is equal to ACW. So let's determine our CW first the simple thing. So this is T, right? So this T, you look at the direction of the tension force right here. So it's actually towards it's like here in this direction, right? So this thing is causing a CW moment. Okay, let's write down the force times distance, right? So force times perpendicular distance. So of course you can see that it's not perpendicular. The force and the so-called distance 1.2 is not perpendicular. So means I just use the FD sine theta. Okay. So force is T. What about the D? The D is from the force. So these are force. Then to the pivot, meaning is this part, 1.2. So it's 1.2. But of course not to forget our sine theta. So sine theta. So what is the theta? Theta is actually this angle right here, between the force and the D. So the theta, if you look at this, 90, right? Then let's see. Do I have other? Okay. Wow, this one a bit. Okay, this one I need to use Tuakaso to determine. So okay, so this is your theta. So I want the 10 because this is oppo, this is adjacent, so it's tan theta equal to oppo, so oppo is 1.6, right? Divide by adjacent 1.2. So let's solve for the theta. Okay, so the theta is in terms of 1 dp, 53.1 degree. So this is 53.1 degree. Okay, what about the anti-clockwise moment? So now I already know my clockwise moment, right? In terms of t, so my anti-clockwise moment, my anti-clockwise moment is the 150 one. So this one is the 150 because you look at this, right? It's causing a ACW. Okay, so let's write down the anti-clockwise moment 150. So this is the force. Then the distance is from here. So from here, use this, from here all the way to here. So meaning is 1.2 plus 0.6, about 1.8. So this is 1.8. Then after that, sine, what about the sine theta? Okay, sine theta, so likewise, the theta is right here. So quite obvious, right? This one don't need to use Tuaka, so you simply just use 90 minus away 10 degree. So this will become 80 degree. So it's sine 80. So this is sine 80 degree. So now I know, what is my anti-clockwise moment already? Okay, so with this, I simply just calculate already. So do a quick one. Divide by 1.2 sine 53.1. Okay, so my tension force, my T is equal to 277.0864.016. So 3SF is 277 Newton. So you can see quite fast. The T, I can simply just use the POM to calculate your T. So of course you can also use the resolution of your vectors, but that one a bit slow already and many steps. But I believe you will still get the same correct result. Yep. So that will be the answer for part C. I think so that's all for this question.